My name is Ravindra Duddu. I put my pronunciation there just as a tribute to Vanderveen, who's fracture mechanics and of glaciers and all informed me a lot when I was learning this stuff. So, and thank you for the organizers for inviting me. So I'll get started with an acknowledgement of all the funding agencies that helped, and also all the early career researchers, PhD students, and collaborators, without which this work wouldn't have been possible. If you recognize your face in these photos here, then thank you for joining and thank you for your collaboration. And if you don't recognize your face in this, then thank you for joining as well. And with a team like that, with a group like that I've just shown, we can accomplish a lot. So since 2021, a lot of publications came out through these collaborations and PhD student theses and all. And I don't have time to go through all of this. And I'll present a few of these, the works from a few of these papers in today's presentation. And if you are more interested, then please contact me at my email, and I'll be happy to discuss and go into detail in any of these publications that came out. So the outline of my talk today is as follows. I'll begin with an introduction, broad motivation and significance aspects. Then I'll focus on three applications. So first, how do we use the phase field fracture model to propagate and simulate the propagation of water-filled crevasses? This is more of a theoretical exercise with idealized domains. Then I'll go into hydraulic fracture of glaciers. That is primarily the work that Tim Hackman at University of Oxford led in collaboration with me and Emilio Martinez Pineda. And there we actually do idealized simulations, but then we connect it to a Greenland Lake drainage event. So that way we are bringing observations to modeling. And then I'll present on the rift propagation in shallow ice shelves that was led by Alex Huth, along with collaborator Ben Smith. And there we use a continuum damage model, but then apply it to a Larsen sea ice shelf. And there we actually do data assimilation and bring in data to actually inform the forward model. So sort of different sorts of levels of incorporating data with modeling. And then I'll make a few concluding remarks. To begin with introduction, I don't need to tell this audience that we have two polar ice sheets. Usually when I'm giving this talk on an engineering department, a lot of them don't know where the Greenland is and where the Antarctica ice sheet is. And so we have them together holding roughly 65 meters of global sea level rise equivalent. And so when I usually say that number of 65 meters of sea level rise, that usually shocks some of my engineers, right? So a lot of water. And to come to the fracture part, ice shelf fracture indirectly contributes to sea level rise, even if not directly. So if you look at this conceptual diagram, you have the grounding portion of the ice sheet, and as it meets the ocean and ice is less dense than water, it starts to float, and because now there is no basal friction, ice starts to flow faster. That leads to flow-based thinning, but then it also thins due to the water melting it, which we call basal melting. And then as it begins to thin, it also starts to fracture. And then near the terminus, it starts to break into smaller icebergs, which we call iceberg calving process. The fractures on the surface are called surface crevasses. The fractures in the base are called basal crevasses. Usually for basal crevasses, you need hydrofracture. That means that the ocean goes in and has to pressurize these fractures so that it overcomes the gravitational closure of these fractures. And whereas on the top, the surface crevasses are mostly not water filled, but except in a few regions, they could be filled with meltwater, which happens due to warmer conditions on the surface. And then when that meltwater flows in, it's going to add additional stress into the fracture so that it can drive the propagation deeper. So there's a lot of mechanics going on here in terms of water-filled fractures that can either destabilize the ice shelves, or on somewhere deeper in the ice sheet, they can connect the surface hydrology with basal hydrology by connecting surface water with the base. So all this mechanics is important because fracture from Greenland and Antarctica ice sheets is a major contributor to sea level rise. The frequency of these calving events is increasing. In the last decade or so, we have seen more of these events happen. And the projections are for the end of the century is that Greenland may contribute 4 to 13 centimeters and Antarctica ice sheet somewhere around 20 to 200 centimeters. Sorry, I didn't put the references for this as they were from multiple sources and it cluttered the slide. But what I wanted to point out with this is that there is a lot of uncertainty. That means that 4 centimeters is 3 times the 13 centimeter upper limit estimate. And for Antarctica, it's 20 centimeters and 10 times 200 centimeters is the upper limit. That means we are talking about huge uncertainties, and we want to narrow down this uncertainty through better modeling and perhaps some other mathematics related to uncertainty quantification, so that we can then drive policy. So now coming to the ice shelf mechanics itself, stepping a little bit from the bigger, broader motivation into more of a scientific description here. So you have different ice shelves exhibiting different behaviors in terms of calving. And partly this different behavior is the reason why we have such large uncertainty. So if we have one mechanism triggering versus not triggering, it could change the sea level rise by an order of, if not an order of magnitude, by a multiple, correct? So then if you look at the Larsen B ice shelf, we described that as explosive disintegration. This is in a paper that Jeremy Bassis led as a review paper that I was involved with from last year. And the explosive disintegration is believed to happen where there was a little bit of melt ponding, and then the water was there, and then that weakened, or rather that pressurized the fractures, and suddenly everything broke up into smaller pieces. The entire ice shelf just broke up. Whereas if you look at Thwaites Glacier, what it seems to describe is small icebergs calving on regular basis. So you have, or maybe a large iceberg then breaking up into smaller icebergs, but eventually there is some sort of a sustained calving happening. And now, if you look at the other side, like a Brunt ice shelf, then you have very large rifts propagating, and you have large tabular icebergs that come out that could be the entire, say, area of London metro area, or the entire state of Delaware in the United States, or the entire island of Manhattan, depending on what you're comfortable in terms of the size of these icebergs. So now, can we have one model that describes it all? And the other aspect is this bar at the bottom, it says weeks to decades. That means that while these explosive disintegration events happen over weeks, the larger rift propagation events happen on decades. So that also shows that there's not only a size scale variability, but there's also a time scale variability. And that complicates the problem further. In terms of modeling, we always looked at fracture propagation in a rather simplistic sense. And we looked at 2D in the vertical plane. And we said crevasses are fractures that propagate, say, in this case, surface crevasses. They propagate from the surface of the glacier to the bottom. Um, and so here I'm showing an image of Ross Ice Shelf in West Antarctica. And this can be modeled with plane strain assumptions and fractures going in 2D. So that's how we typically operated. And some of the earlier works like zero stress approach proposed by Nye and others, and then Van der Veen's fracture mechanics approach and so forth, they all focused on this 2D problem of how deep is a crevasse going to propagate. But then on the other end, you have these huge rifts, which are almost full depth fractures that propagate in the plane of the ice shelf. And here I'm showing the Larsen C ice shelves fracture, and you can model them as also 2D fractures in plane, but then applying these boundary conditions of how the forces and all due to the gravity and stuff, they become complicated. So the objective of my work has been that how about we represent fracture propagation as a unified three-dimensional process related to the creep deformation, not just the elastic stress state, the current material state, and then propose it as an evolution problem, a dynamic evolution problem, so that we get from small fractures to large fractures in the time evolution, and not just in terms of linear elastic fracture mechanics or zero stress, where there is no time in those models. So that has been the goal. And with that goal, we started on several different directions. So the first direction here I want to talk about is just those 2D crevasses, if they're water filled, and using a phase field fracture model instead of a simple linear elastic model. And the questions that motivated this type of work are, one, can hydrofracture, that means that when meltwater goes into these surface crevasses, can that lead to full depth penetration? Part of this is answered already through some simple linear elastic fracture mechanics, but we are looking at what phase field tells us about this. The next question is, how does surface crevasse spacing affect crevasse depth in the glacier? And this is the part that neither the Nye zero stress or the LEFM models particularly describe because of various reasons. We get into it if anyone's curious. But before I go into the phase field, I want to talk a little bit about what the so-called poro damage phase field model does. So the phase field fracture model is a diffused interface approach to modeling fracture. That means, let's say you have a body here, which I'm showing in the small sketch, and you have a fracture in this gray colored region. And normally you would describe that fracture as a sharp interface. That means it's two surfaces that are created by one crack. But in phase field, you're going to describe that as this diffuse zone, which has a width approximately of 2 times this length scale that is a regularization parameter in the model. And then you write the energy contributions of the bulk solid due to the elastic strain energy, but now you modify them with D, which is that phase field or damage variable. And you also write this crack surface energy, which is the second term, which is related to the region where the crack is diffused. And there, what we are saying is that the opening a crack requires this GC, which is the Griffith energy or fracture energy corresponding to a material's property. And then the third term is essentially body forces and any external forces that also contribute to this stored energy, right? And so if you start with this energy and then you minimize them with respect to the unknowns, in this case, our unknowns are We want to solve for the damage variable that tells us where the fractures are, and we want to solve for the stress which drives this damage. Then we take those derivatives with those two variables, in this case, displacement corresponding to stress and damage corresponding to the phase field evolution equation. And then we also incorporate Terzaghis principle, which is known in geomechanics, to incorporate the effective pressure in the case when we have water in the water-filled crevasses. So an additional term comes in PW here to make this equation consider both the solid stress, the fluid pressure, the gravity, the self-weight of the glacier that causes the resistive stress in the glacier, and then HD, which is the crack driving force that is related to the stress that then drives the crack propagation. So we proposed this model in our first paper on phase field fracture with my PhD student and postdoc Rishikesh and son. And then that led us to another slightly related model, where we use a stress-based crack driving force. And that was proposed by Clayton and Emilio Martinez Pineda, and that got published in Engineering Fracture Mechanics. So in these two papers, we laid out the theory and the benchmark for this model. And what we see is that for simple cases where you have a rectangular glacier, you have one crack that is filled with water to a certain height, HS, but the crack depth is ds, and you have an ocean water pressure because it's a ocean terminating or marine terminating glacier. Then you have HW. And in that simple case, what we are trying to say is, how does the crack then propagate from this pre-existing defect, and how deep does it go, right? And what we found out is, depending on how the meltwater depth ratio changes, that is, this is the amount of meltwater filling the crack, the depth of the crevasse will change. And that also is related to this ocean water height. So then we considered three ocean water heights. HW is equal to 0, HW is equal to half the height of the ice, and then HW is 0.9, the ice thickness, which corresponds to near flotation, correct? And in all of those cases, we ran for each of these dots that are circles that you see in red, blue, and green. We ran one phase field simulation. And then we calculated the corresponding linear elastic fracture mechanics depth. Think of this as, Vanderbilt fracture mechanics model. And using that, we can figure out the lines, which are the analytical depths. So this is our sort of numerical verification. As close as it gets, we have an analytical model, and then we have a simulation, and then we are making sure that in the simplest of the simplest cases, our model is matching the analytical understanding. And so indeed, we see a good match for all different seawater heights and all different meltwater ratios. And the general trend, what we see is, as you fill up a crack, and let's take this 0.5 case, as if there is no water, you get only 40% crack depth compared to ice thickness. But as you increase water and you fill it up with maybe half of the crevasses filled with water, we were getting full depth crack propagation. That means that only a partial amount of water, in this case half, is sufficient to cause enough driving force to cause full depth fracture, right? If there is no water, then you won't get full depth crack propagation in this case. But and the other important point is, if you're very close to flotation, then even if you filled it with water, you don't get crack depth. And what this meant is that the reason why hydrofracture doesn't happen all the time, even when there is water in the crevasses, is precisely because of that. That means that when the broader stress conditions are compressive and not too tensile, then you can have standing water in these crevasses. And that's because we don't have enough driving stress that is just uh, supplemented by a small amount of water. Okay, so that's good to know. And then the next thing we said is, okay, that was an isolated crevasse. What if we had multiple crevasses, sort of like the Nye zero stress case, right? And we do see that when in this situation, you get most of the cracks propagating to a depth that is similar, but you see that the extreme cracks obviously have some variability. They propagate to a deeper extent. And this goes back to the debate that de Robin and Weertman had, and how zero stress model is sort of an academic exercise that crevasses are never uniform, right? They can never be a uniform, exactly same distance, depth systems in crevasses. There's always this physical variability. But the gist is that if you do the same exercise of taking the meltwater ratios and crevasse depths, you get the same behavior, that when there is no meltwater, you have a smaller depth of crevasses. As you fill it in, now you get to full depth propagation in the 0.5 H case. And in this case, we compared the zero stress model depths with our phase field fracture simulation, and you get good matching. But I haven't shown the zero seawater case, because in that case, what happens is some of these anomalies in fractures make it propagate all the way through, right? So that means that when the driving stress is really large, then zero stress model generally doesn't seem to apply very well for even for closely spaced crevasses. And so that's why we haven't included that result in there. So this was a very interesting exercise. So then what we did was, hey, let's do it in 3D and try to see how crack interactions happen in the space, because this was our objective, right? To see crevasses and rifts in this one unified 3D formulation. So this is a paper we just submitted to Journal of Advances in Modeling Earth Systems. And I'm showing a couple of results where we take the same phase field formulation with some brief modifications, and we do isolated crevasses in 3D, which first propagate from the surface to the depth, and then they start propagating in plane and sort of forming these precursors for rifts, right? And the exercise here is that if you have crevasses that are widely spaced, then they will grow as isolated rifts. But if you have multiple ones, closely spaced, then you start to see interactions among them. That means some crevasses did not propagate, some propagated and coalesced, some propagated to certain extent before they stopped and did not coalesce, and then some are trying to curve and join with their neighboring cracks and not the crack straight ahead of it. So this is interesting, and what we thought from this is that if in a closely spaced crevasses, these other rifts from or other horizontal crevasses, if I can say that, they all influence each other. And so if you were to just apply a zero stress model locally, that means that if you were to take a point here and say, at that point, what is my stress field? Will my crack propagate? Then you're potentially missing the interactions that come from these spatial interactions between cracks. And so there is a utility in high fidelity phase field models in understanding how crack networks evolve and how does that contribute to calving in terms of, does it increase calving, or does it actually restrict calving of icebergs? So I want to add one last point, is that these were intensive simulations. So we had tens of millions of unknowns or degrees of freedom. So we had to run these in parallel. We had to use adaptive mesh refinement algorithms. We put this all into an open source finite element software, Phoenix, and that's all packaged into this journal article. And we also have shared all the codes in Phoenix that we have using GitHub, and also the data on Zenodo. So if you are interested in using this model, please get in touch with us, and also you can look at those online repositories. And finally, one nice result is the effect of boundary conditions. So if we have boundary conditions that are varying, for example, in this case, this top boundary or the back boundary is fixed, the front boundary is free, and in that case, you get that the crack propagation is curved, and you only get cracks near the terminus. So this is the ocean interface, and this is the far field interface. And so crevasses form along the margins. So there is a shear margin type development that we can see here on the back face. And then the curves near the terminus curve. The cracks near the terminus curve. Whereas if at that point something were to happen to the back boundary and say the shear margin somehow becomes very weak, and so it becomes from fixed to free slip, then that sort of changes the stress field so much that now you start getting these sorts of crack networks, crack branching in the rest of the glacier, because now the glacier is speeding up. So lateral margins, when now suddenly they change from free to slip, now you can get polygonal fracture patterns. And how does this match? If you see the real observations, and this is always our exercise, right? We take modeling and then we want to connect it with observations as much as possible. And in this case, we see some cracks curve. This is a Greenland glacier. Please, if you know the name of this glacier, do message me in the chat. And you have evidence of these curved fracture patterns. But if you also look at this, which is from Thwaites Glacier, then you also see these polygonal patterns. So I'm not saying that we exactly are capturing the same mechanisms in both of these cases, but it seems like there are some mechanisms with boundary conditions that can cause these types of stress states and crevasses. So this is encouraging that our phase field fracture model represents the true complexity and reality of crevasses, and not just the simple idealized analytical expressions. So how did we do on the questions? Yes, if the seawater level is low and the crevasses are filled with water, you can get hydrofracture full depth. But if you have a near flotation glacier, there is enough compression to prevent hydrofractures from fully forming under certain stress states. So that's why you see ponding of lakes, because the driving stress is not enough in those regions to propagate full depth fractures. Now, then crevasse spacing obviously affects these crevasse depths, and that is the mechanism we call crack shielding in engineering. And so we do see this evidence in simulations. So let me move on to now the second topic, which is hydraulic fracture of glaciers. Here we'll focus on a much more advanced model for hydrofracture. So the motivation here is that if you see the surface of Greenland, you have these lakes filling in and suddenly draining out, and these happen in somewhat of a cyclical process. And the questions always come up from a mechanics point of view is, does the rheology of ice, the fact that ice is viscous over long time scales and elastic on shorter time scales, it's just an assumption. In general, it's a much more complex viscoelastic material. So how does this ice complex rheology affect hydrofracture? That was a question we first posed. But more of an observational question, why does the surface elevation change during lake drainages? So people have put GPS stations around these lakes, and then as soon as the lake drainage happens, they see a surface uplift, right? So what is happening there? Why does a lake drainage cause the surrounding regions to lift up? And to answer that question, we formulated a simple model where we took the original complexity of a lake having a um, so a lake having a complex shape, not necessarily a circle or anything like that, and also the crevasses having elliptical shapes as they propagate from the surface to the bottom. Too complicated. There's too much going on in terms of the water either being able to freeze in the cracks or able to induce frictional heating and melt the cracks open, or you can have turbulent fluid flow that actually causes the frictional heating. And then there is conduction of heat from the liquid water to the solid ice. So there are all these processes happening. So we make simple assumptions of plane strain, thermal equilibrium, and ice has no porosity, and so forth. And then we simplify it into a 2D model. And now we can only take the vertical section and just do a 2D simulation. So we don't have to fully resolve the out of plane width. So this is the work that Tim Hochman, who I believe is in the audience right now, has led this work. So majority of the credit to him for figuring out all these complex equations that define that process. I won't go through the entire equation set, but just want to say that this is a 2-scale model. That means if you take this rectangular glacier sitting on top of the rock that I'm showing on this figure, then that is our 2-dimensional math computational domain. But the fracture is just a line, which is this vertical line that I'm showing with my cursor on the screen. And so we don't want to resolve the fracture with the same type of mesh size and 2-dimensional mesh as you would do for the entire ice domain, because that would then become prohibitively expensive. And so we make it 2 scales. So when we solve the glacier scale problem, the fracture is just a line and it's an interface. And we just solve for momentum balance, stress strain relationships go into that, and definition of viscous strains using Glen's law. But then we're solving the mass balance only on that line for the fluid flowing through the fracture. And then we are going to go into the fracture scale, which is at this inset figure, right? And there we establish some coordinates to then figure out how that opening of the fracture is related to the flux that is coming in, that this mass balance gives us. And also we have this displacement of the ice, and the displacement of the ice on either sides of the crack, the difference or the jump gives us the crack opening. And that's called the crack aperture relationship. And then we put in some turbulent fluid flow equations for frictional, the friction aspects, which then go into the thermal problem because it causes frictional heating. And so all those equations then give us a full picture of the complexity of this hydraulic fracture, which goes turbulent. That means that the water, as it's flowing from the lake to the bottom of the glacier, it is going to have the Reynolds numbers reach very large numbers that it becomes turbulent. So then we compared it with the data out of Sara Das's paper, where we took the ice glacier thickness, and this is the Paktisok region, I believe, of Greenland, where there's some GPS stations that were put. We have some data from that. And then we have some estimates of what the lake surface area is, and then the ice height and so forth. And then we also took some borehole data measurements from another paper for a nearby region. We got the Glen's exponent for the creep coefficient. We got activation coefficients from some other reference. And then we also said that the tensile stress of glacier, or strength of the ice, is also dependent on this temperature. So we got some empirical data for that. And we put all that together and we ran the simulation, where what we see is that with the elastic rheology, if we neglect the viscous components, right? There is no viscosity of ice. Then you get faster propagation of the vertical crack from the top when the water is filling the lake. But then once that happens, there is not much deformation in ice to actually let waters go underneath the glacier and lift it up. And so essentially the glacier, the crack propagates, and then it really stops. The process stops. But whereas if you take the viscoelastic rheology, the water goes in. Let's start from the beginning. It's much slower because of the viscous nature of ice. The stress concentrations are smaller. But then as the deformations increase with time due to creep deformation, you get the chance for water to go underneath the crack and form a blister. And that causes your surface of your glacier to increase. And this is why the GPS measurements show that there is an uplift. So what did we find from this? That vertical fractures filled with water propagates better with, so linear elastic, it propagates faster, but viscous rheology, it propagates for longer to actually cause a blister. And we also compared it with these observations. And I don't want to go into the details in the interest of time, but linear elastic doesn't match with any of these lines, which are observations. But if you plot the observations, the red dashed line against viscous, then the red dashed line matches better with one of those simulations, and it's within that range. So that's an important point. And also we found that if ice is much, much colder, say, let's say colder than -7 degrees, then the refreezing of meltwater shuts the fracture process. But if it is warmer, then you can have a full depth fracture. So that means that we also need to watch out for temperature and of the ice. And if warmer temperatures of ice are found in other regions which are much farther away from the terminus, then we could potentially have fractures in upstream regions as well. So quickly to summarize this, how did we do? Yes, ice rheology matters, and it leads to effective drainage. So viscoelastic rheology is important there. And then the elevation is also related to this hydraulic pressure that goes and creates this basal crack underneath the glacier and then forms the blister and lift up the glacier. And that's why elevation is changing. So that's sort of, in the next maybe 5-10 minutes, I'll try to finish up the third story as well, which is rift propagation. I may not fully be able to do all the details, and hopefully I'll have some questions that we can go into later. So the motivation here is we saw the Larsen C rift take an arcuate path and gave rise to this A68 iceberg. So why didn't it have a straight fracture? Why did it curve? Right? So that was a significant question. Why did it exactly take that specific path and not another path? And then if you look into these fractures through a flight, I've never done that. Would love to do it if someone would offer me a seat. How does this internal properties of that rift due to the melange in there and due to the seawater influence the rift propagation? So those were the two scientific questions we started with. And to do that at that scale of Larsen C ice shelf, we couldn't have done a full Stokes or a full stress 3D stress solve like we did before for the phase field. So we had to work with a shallow shelf approximation. And in this case, like as you know, it's in the ice shelf, the shallow shelf is much, much more valid. But whereas deep inside the grounded portion, you would use a shallow ice approximation. And using that, you can get velocity, right? You're solving two differential equations for V1 and V2, which are the in-plane velocities. And then that gives you the deviatoric stress, then you can analytically get the vertical stress is hydrostatic, and then you can add that and now get a three-dimensional stress state. And then you can add water pressure, hydraulic pressure into the cracks using an empirical sort of expression. And that gives you crevasse depths based on this creep damage model that I worked on in the last decade as a postdoc at Columbia. And then that once you know the crevasse depth, you know how much of it is intact and how much of it is fractured. If you follow my mouse here, right? What is the initial state? What is the final state? What is the crevasse depth? And then you take the some damage approximation of that, put it back into the shallow shelf approximation, and degrade the viscosity in those regions, and then you run this over multiple time steps. And that's how it works. Now, these are those underlying equations, too many to get into. Some of you may be familiar with this, some may not be, so I'll save time by not going into details. You can read these part 1 and part 2 papers with Alex Huth, me, and Ben as authors. And the important point I want to say is we include seawater pressure in basal crevasses through some parametrization introduced by Keller and Hooter in 2014. And then we also use this creep damage model that also takes into account the brittle and ductile type of fracture processes that can happen in ice. And then we depth integrate the damage to put damage into the shallow shelf. So the first benchmark we did to see how this works out is the MISMIP plus case. This is in the second paper of Alex Huth in James Journal, if you're interested. And the MISMIP plus has this interesting bed geometry where it's floating in these red regions and the other regions where it's actually grounded. And what this is showing is the top surface of the ice and the bottom surface of the ice, right? And so that's how the glacier looks in 3D, but we are solving this in shallow shelf. When we incorporate isotropic damage, what you see is that you see a lot of damage happening near the grounding lines and some between around this grounding line in the floating regions. But as we increase the anisotropy of damage, so what we are saying is that fractures only happen perpendicular to the direction of the max principal stress. So if we introduce that physics into it, then you get arcuate crack patterns. And those arcuate crack patterns represent those which we see in reality with Pine Island Glacier, for example. So that was sort of the main conclusion from that work. Then we did a lot of inverse modeling to sort of apply it to Larsen C. Again, in the interest of time, I will just say that lots of data sources. The paper is published in Journal of Glaciology in 2023, and we do like a inverse model to estimate how the initial state of the ice is, the viscosity and stuff. And what we found is that if you don't include those Gibbs ice rise and Bowden ice rise, which are at the extreme regions shown by these circles here, red ovals rather, you don't get the right velocity field when you do the inverse. So that's an important point. And then we do that inversion, we extract damage. We also do a second inversion to get this enhancement factors, which are probably related to the anisotropy of the ice fabric. And then when we run this forward model from 2014, where we have the initial state, and then we run the simulation forward, and the question we are asking is, can we get the exact shape of the iceberg? And as you can see, the current model is able to give us a reasonable crack propagation that takes us from this initial state to the final state, right? Looks really nice, but you may ask the question, you're only showing me the case where it doesn't work. or it does work, but what about the cases that it didn't work? And that's where I want to come to this concept of the melange and the seawater pressure in there. And if you incorporate melange and seawater, then that changes the stress state uh, at the crack tip. Okay, and that can be parameterized in different ways. So that's given in detail in the 2023 paper. And what we found is this, that if we assume melange is weak and ignore water pressure, you get a crack path that does not match with observations. But if you assume melange is strong, or if you include seawater pressure, then you get the right crack path. That means that one of these two things is happening. And we mostly think that the seawater pressure is a major factor in changing the stress state near the rifts. But there is some effect of melange at the crack tip that also, or in the healed regions behind the crack tip, that also cause these changes. So melange and water pressure seem to have an effect. So how did we answer? And this is how I'll end. Uh, so yes, the crack path curves relate to the locations of these ice rises. So they're very important to how the stress state is and how rifts propagate. And so we need to be looking not just where the ice is, but also what is underneath the ice shelf to get a better picture. And then the melange and seawater also influence the rate of propagation and the rift path. So to conclude, I would say the key takeaways are I presented this phase field fracture model that can predict depths of water-filled crevasses. It shows evidence of crack shielding. So Nye and LEFM are only an approximation. We should probably use high fidelity fracture models to get an in-depth picture. Then the two-scale flow fracture model does a good job with the hydraulic fracture propagation in Greenland glaciers and highlights that we cannot ignore viscosity. We can't just simply say that fracture is an elastic process because the viscous processes affect the propagation as well. And then finally, the creep damage model, along with shallow shelf, can successfully reproduce iceberg calving events. The next thing that we are looking at is to replace this creep damage model with phase field fracture model and see how that works out. So thank you all for your attention. Sorry if I went a little bit over time, and I'll be happy to have any exchanges with the audience now. Yeah.
Great. Thanks, Ravindra. That was excellent. And you were right on time. You're right on time of what you had expected. So you're good.
Thank you.
I'll open it up to any questions. Again, you can drop them in the chat or feel free to raise your hand and unmute yourself, and I'll pass it over to you. Yes, Mohammed.
Great talk, Ravindra. I was wondering about on slide 26, 26 or 27,
Mhm.
For the uh, viscoelastic
Mhm.
model, are you also assuming a temperature dependence on the viscosity, or are you
Mhm.
assuming a constant viscosity?
Yeah, so that's a very good question. And so if we go to this borehole data, what it shows is that the temperature at the base is almost zero, but on the surface is something negative, but it varies with depth, right? And so what we do is we corresponding to that, we take the viscosity as temperature varying based on the Glen's creep coefficient defined by an activation energy. And then the tensile strength also has some variation with respect to where it goes to zero when its ice temperature is zero almost, and then it increases for when ice temperature is -10. Yeah. Does that answer your
Yeah,
question?
that
Yeah.
makes sense. Thank you so much. I
Yeah.
have one more question, if that's
Yeah.
okay. All
Yes.
right. On slide 17, I was wondering, you were talking about the boundary conditions, and on On the left one, you have, and on the top side, you have x directional velocity equals 0. But on subpanel B, I was wondering what's the boundary condition? Is it on the stress, or are you assuming a non-zero x
Yeah.
directional velocity?
Yeah, this is a little complicated one, and I think I didn't do a. It's always hard to explain this, so thank you for asking this. So what we did in this case is first we took this rectangular domain, and we started off by fixing that back face. That means at all nodes on there, we fix the displacements because this is a linear elastic formulation. We don't have velocity, we have displacement. And so we fix both the horizontal velocity and that out of plane velocity uy, right? And that makes this surface very stiff, and so the stress concentrates, and you get this shear margin like crack. And what we said is, okay, if we don't change the boundary condition, then we don't get any more interior crack propagation. We only get it near the terminus, and that's it. That's the end of the simulation. But now we ask the question, somehow, let's say at this point where the margin weakens, so then we just removed the constraint on ux and let it slide in the x direction, but we just said that it cannot move in the y direction, right? Because there is some other margin or something it's preventing it to go laterally. And so if we change the boundary conditions at this point and take that as the initial case, then we get this other format. So that is sort of clear where this is our starting point, and then when we change the boundary conditions, suddenly you get these other fractures. So the reality is that when you see something like Pine Island Glacier, there's always some sort of motion over long term, right? The margins will always move as the ice is flowing. And so suddenly you will have a transition from a fixed condition to a free condition. And then that changes the stress state suddenly and propagates these sorts of fractures. So what our hypothesis is that the changing boundary conditions is the reason for these patterns. So if that makes sense.
Thank you so much for explaining this, and great talk. Thank you very much.
Thank you, Mohammed. Appreciate it. Yeah.
Thank you, Mohammed. Michael.
Hi, Ravi. This was an amazing talk. And back on these slides, I'm always thinking about like basal crevasse geometry too. So if you change the boundary conditions I'm assuming I think this is a surface crevasse experiment. But if you ran this like for a basal crevasse, you also suspect that the geometries will change in some funky way for those.
Yeah, the running the basal crevasses is always quite tricky because you have to figure out the floating of the ice along with where the ice will float, and then how the water will then go into the cracks and stuff. So it has always been a tricky exercise for us to simulate. So I don't have any 3D simulations of basal crevasses. But what I would think is that you could get some transverse basal channels affecting the basal crevasses, and now you're having these networks of basal crevasses coming out of those other features that exist. So that's an interest. We haven't really done much modeling on basal, but we will keep you posted as we make any progress. Yeah.
Awesome. Thank you.
Great. We're almost near the top of the hour, but anyone else? Oh, there we go. Mohammed again.
I have one sort of selfish question. I was wondering if you have looked at fractures of ice layers within firn. So not exactly ice sheet, but within firn. And yeah.
So not in the context of phase field from my group, but Tim, who's perhaps still in the audience, has looked at that, and he was looking at fern as a porous, elastic, poroelastic material, and then looking at flow there. So he'll be a good person to reach out to. But this paper from 2024 with Clayton in the cryosphere, we used a linear elastic fracture model to look at fern and whether the porous layer makes a difference for fracture. But it's a very simple analytical based study, and what we find is that the fern layer actually makes fractures propagate deeper in floating ice shelves. So both the Gao paper in 2023 and Clayton paper in 2024, so number 10 and number 6, both showed that fern has a huge impact on fractures in floating ice shelves.
Thank you so much, Ravindra.
Yeah.
Really appreciate it.
Yeah, sure. Thank you.